grab your coffee, and if I could have the other folks come up here to the front, that would be great. Yeah, go ahead, come on up, guys. Got Francina, you want to come up? Yeah. And see, John. Where's Ruby? Is that?
Oh yeah, where'd Ruby go? Yeah, she heard you wanted her on stage.
Yeah, she vamoosed. Okay, we got Ruby, we got Francina, we got Jim, and who else is here? Yeah, okay, Jim, that'd be great. Francina, we got Andy's coming up. Ruby, okay, great. All right, well, we had fabulous discussions yesterday, but I've been talking way too much, and I'm also not the subject matter expert here. We thought that we would start today by talking about things that we all agree on. That always is a really good place to start. And not that there are any violent disagreements or anything like that, but there are some things that I think we have to better understand. And so what we're going to do now is spend some time really talking about really where we want to go and how to best get there and what the pathway is, if it's a phased approach or whatever, but really to start with what we all agree on. And that will bring us to, I think, the things that maybe there's a divergence of views on and opinions and things like that. And so we got the planning committee up here plus a couple others. Ruby, you want to go ahead and kick us off? And we sort of corralled her, and I'm gonna sit here and take notes, but we're gonna have a good, robust discussion. And feel free to clearly use the microphones. We have, I think Bjorn and Tim and other folks are online. So yeah, we can't, unfortunately, we can't put the Zoom people on the screen, right? Unfortunately, we can't do that. For whatever reason, we're not able to do that. It would be good, but they are with us. So okay, Ruby, go ahead.
Okay, so I'm not sure where I'm starting off, but I'm glad to do that. So so I think the summit has been going really well. So we have
yeah, the mic's not working, Ruby.
No.
It'll be on.
All right. So you can hear me? Yeah. So first of all, I want to say that I feel that the summit has been going well, and I've been hearing a lot of ideas and opinions from the broad community. I think this is great. But I think maybe one thing that seems to be a little bit inconsistent, but potentially we can get some consistency on is really the resolution that we are shooting for, right? So I think this summit, of course, is talking about kilometer scale modeling. Kilometer scale doesn't necessarily mean 1 kilometer, but normally it would mean something of the order of 1 to 5 kilometer. I don't know if people agree with me on the definition of kilometer scale. But then, of course, there have been also discussion about, hey, it's easier to get to 10 kilometers first, and then we can do downscaling, and that is also a great idea, right? So I think the question is really, do we agree that ultimately that the higher the resolution, the better? Let's say if we have a big computer that we can use to help us better tune the model, and also resources for people to continue to improve parameterization, like Carmichael physics, like turbulence, and things like that. And having a big computer to help us really address a lot of these problems related to parameterization. So I think we all agree that whether you go to kilometer scale or 10 kilometer or 25 kilometer, we all have problems to solve in terms of parameterizations. But the higher the resolution, I think we also agree that, and the less reliance on parameterization. I think it's something that at least if we can get some clarity on what's our view on where do we want to get to ultimately, might be a good thing to do, and then we can discuss like how do we get there, right? So I think we have been talking a lot about challenges that we are facing. It doesn't matter whether it's 10 kilometers or 1 kilometer, we are facing a lot of challenges related to parameterizations, related to model coupling. We all agree that we do not need just atmosphere model. We need the fully coupled system, especially the ocean and sea ice, which is part of the big. So I think maybe perhaps some discussion related to this could be useful. Is it not here?
You're cutting out a little bit.
Oh, okay. Sorry.
So do we all agree that
Kelvin, can I just make a few?
Oh, I'm sorry,
comments
Jim.
on
Yeah,
that?
I just want to make sure that, okay, yeah. Go ahead.
Well, no, because I just wanted to sort of add to that. So I just
Yeah.
wanted to say, I agree with what Ruby has said. I think we have an opportunity here. I think a step forward would be if we can have a discussion and come to some agreement on what our ultimate target kind of resolution is, kilometer scale is, I think the way that Kelvin has framed this summit and the opportunity that we have before us is to do something truly transformational or be thinking about what we can do that is transformational. That is not to say that there are not a lot of questions and a lot of issues and a lot of technical challenges and a lot of research and development that needs to be done when we think about developing fully coupled systems at kilometer scale resolution. But what we've put on the table here, I'm not part of the planning committee. Kelvin just said, get up there today. So, but I think there's an opportunity here, as we emphasized yesterday, to follow a different paradigm where if we can present a shared and exciting vision of the kind of step change that modeling at these scales can provide, there's an opportunity to raise a significant amount of money to develop a computing system or provide that kind of computing platform where a lot of this work can occur. If we don't kind of come out of this with that kind of a transformational view, then personally, I'm skeptical that we can achieve what we're hoping to achieve here at the summit in terms of a machine. So I just want to endorse that. And I think that, I've seen enough, I've heard enough, I've been part of enough discussions over the years that I think aiming for kilometer scale coupled modeling is really what we should be doing here.
I think one of the most important things that we get by going to kilometer scale in the sense that Ruby defined is we resolve the mesoscale. And by resolve, I mean 10 or so grid points across the mesoscale system so that you get a reasonably accurate simulation of it as it moves. You can't do that with a 10-kilometer grid, but kilometer scale grid can do that. So I think that's a strong argument. Jim mentioned transformational. Well, resolving the mesoscale is really transformational. That's been missing in all our models forever, and we need to fix it. And this is how you do it.
From the practitioner's perspective, if we are to provide information that they need for extreme weather and water resources, we need to get to the mesoscale. So I think that we have to go to the kilometer scale. 10 will not cut it.
I just think we also have to look at all the other efforts that we've read about in Europe and Japan, and we're certainly not doing something transformational if we're not at least living up to the same level of ambition as they are. And MPI is already doing 5-kilometer coupled modeling, so I don't think it's transformational to do 10-kilometer modeling, given that the points that Dave raised about the advantages of going to kilometer scale.
So is your feeling that we should be focusing on kilometer scale modeling then?
No, I think kilometer scale modeling is fine, but kilometer scale doesn't mean 10 kilometer scale.
Yeah,
Kilometer scale
okay.
means 2 or 3 kilometers.
2 or 3, yeah, okay. So our target should be 2 or less, yeah.
I don't have a dog in the fight on the scientific angles, but I'll just say we're talking about scale, but we were also talking about speed. Hitting the scales is much easier than hitting a certain integration rate at those scales. So if we have to prioritize scale, I don't think that's hard. Scale at 10 simulated years per day, I think that's going to be a real challenge.
So do you believe that we should be working out what it takes to get to that speed in addition to the scale as both in tandem as we work that direction?
Yeah, absolutely. I think thinking about that, but also thinking about if there are a multitude of models and a multitude of users, you can also get the same amount of science done without having a faster rate for a given run by running multiple runs at once on a given system. It's just something to consider. What is the goal when we talk about kilometer scale? That's not all there is. There's kilometer scale and how many people we're serving at what rate. So.
Similar to that, I want to put in I like the 1 kilometer 10 simulated year per day goal because it's clearly unachievable on current hardware or even envisioned hardware. So it's a great technical, aspirational challenge. I don't know if it's possible. That aspect of it that is appealing in technological point.
Maybe just adding, echoing what Dave just said as well from a science perspective. I think we're really talking about a different class of models here that can resolve this mesoscale phenomena much better, which will allow us to do really novel science and produce data that's very valuable for that community. But I also want to highlight, I think 1 kilometer shouldn't be we can look further down the road and this is not the end point. So we can easily say LES scale, and the Japanese already ran their Nika model at 200 meters. Developing modeling systems that are agile, that can bring us even further. And I think these modeling systems that we're talking about can do that in large extents, and CMIP models typically cannot at the moment. That's why we should shoot for, in addition to the hardware, but also looking at long-term, 10 years out.
Tim has his hand up.
Can I, yeah, thank you. Can I just make a quick point, which I made in my talk, and I think John Petch also kind of made the same point. But I fully agree, of course, with Dave and others about the importance of resolving the mesoscale. But it's important for 2 reasons. It's not just important, if you like, for its own sake. It's important to try to ameliorate the upscale propagation of systematic biases at the truncation, at or near the truncation scale, up to the synoptic or even planetary scale. And this is the problem that, the current generation of models, where the resolution, let's say, is 50 or 100 kilometers, you might think, well, okay, they can't say much about extreme weather on scales of tens of kilometers, but at least they can say something about the statistics of climate on scales of thousands of kilometers. But unfortunately, that's not correct because of the biases that these small-scale processes feed up to the synoptic and planetary scales. So when we talk about monsoons, or talk about blocking anticyclones, or talk about the ITCZ, or talk about ENSO statistics, these are on very, very large scales, but the current generation of models don't do a good job at simulating the observed statistics of these large-scale events. And so for me, for me, even more important actually is than actually getting 1 kilometer scale information is reducing these biases so that they're at least, we should be aspiring to a system where the biases are small compared to the signals that we try to predict or project. And we're not in that happy stage. And that means we're not giving society the best information we can about regional climate. And that's, for me, why we have to take this leap. 10 kilometers is I don't think there's any evidence. There's no basis for saying 10 kilometers is going to do it, but there is some basis for saying 1 kilometer, because we do start to resolve gravity wave drag. Like I said, we start to resolve deep convection, we start to resolve ocean mixing, all these sort of things. So there's a good physical reason for why this will be a step change if we can get to 1 kilometer. And I just think that's good enough. You know, that sort of argument was good enough to sell the Large Hadron Collider. You know, they didn't know the Higgs existed or not, but there were good arguments that it might exist. And I think we've got good arguments that a step change will make a big difference in our ability to simulate climate. And I think that's good enough to go ahead with it. So that, anyway, that's my point.
Thanks, Tim. We got a comment here, and then Bjorn has his hand up, just so you all know.
Yeah, I just wanted to say something I've said before, but trying to refine the thought that bringing these models, focusing our efforts in this domain on the historical period, and really understanding, first of all, the degree to which the models can, help us fill in statistics for variables that haven't been all that well observed, or very sparsely observed, but are really, really impactful for long-term planning and resilience would be terrific. And so kind of exploring the spectrum between like atmosphere only runs and runs that are sort of lightly data assimilating. Maybe it's too hard to build a full data assimilation capability at 1 kilometer with all this, but maybe just nudging things towards the observed surface pressure distribution, which we have for which we have observations all the way to 1940. It's some way of just kind of making the statistics of this as close as possible to the statistics we imagine we would have seen had we observed our planet really, really, to the even better than we can now, all the way back to 1940, and then freeing the model to do a lot of free running scenarios where we start to understand the range of natural variability, so that we can understand the climate change signals that we see in the context of really, really well-defined natural variability for these extreme weather variables that are of so much interest to our built environment and health and safety, that kind of thing. I think that would be a terrific way of focusing efforts for this kind of a tool.
So is that a yes? We should go for 1 kilometer?
Oh, yeah, we should go to the resolution that we need to generate, things like wind gust, and I am hearing that resolution would be helpful to observe those kinds of extremes.
Bjorn, go ahead.
Sorry, do you hear me?
Yeah.
Okay, I just wanted to chime in a little bit on our experience with the throughput. So that came up before, and our experience kind of through the history of some of the IPCC and recent work going to the finer scale modeling has been that if we can get about 100 days a day, that's actually pretty useful. And I think we can do that on commodity machines if we don't backslide further on some of the performance related to our codes. We can do that. So at a kilometer, at 100 days a day. The thing I showed you before, that was about 10 days a day on, 10% of a tier 0 machine. And actually, yeah, so that's doable, and it's a nice target, 100 days a day. If we want to, if the point also is to be transformational in terms of the hardware, then we should phrase it with a higher throughput. And so you could say a kilometer at a year a day would be, and that's a phrasing we'd used before. I don't think that's really doable with the way I see the hardware developing, the codes developing now. Maybe I'm wrong and someone can do it better. But I think that would need something transformational, not just in the resource, but also in the hardware. So think about that. And another thing that's a little bit lost from this discussion is that it might be in the back of everybody's mind, but if you're talking about 100 days a day at 1 kilometer, then you can see what that gives you at 10 kilometers. And we run our models at 10 kilometers, 5 kilometers, 2 kilometers, 1 kilometers, and hopefully at 100 meters soon too globally. And the main difference is how long we'll run them for. And actually 100 meters for a few days will teach us lots about very fine scale processes, which will make the 1 kilometer model run for years to decades better, which will make the big ensembles run at, 10 kilometers much better. And so getting into that range where we can move back and forth, I think Andreas was mentioning that as well. I see that's really key. And so when you phrase this, I think it has to be clear that it's not just 1 kilometer at a year a day. It's that this creates a facility that allows us to solve or attempt to solve really urgent problems. And the other thing that I haven't really heard is that if we're going to be putting out that much output, it has to be linked intelligently to this enormous developing capacity of machine learning for people to find ways to anticipate what those simulations are trying to tell us much more efficiently. So that should be part of the vision somehow. But again, that's probably all in everyone's mind, but I just want to say it explicitly.
Yeah. So I'm certainly, I think we're being very ambitious with the hardware, but I think that we should be. But I think what Bjorn said is that even if we're unable to attain our goal of the 10 simulated years per day, which is our moonshot goal, that it isn't a wasted effort to get to the kilometer scale model, even if you don't obtain that goal.
So anyways, first of all, I want to say as a kilometer scale model developer myself, kilometer scale models are really awesome, but they aren't more skillful. And indeed, this is something the European Center has struggled with. They run their kilometer scale model and they find that the skill scores actually have gone down compared to their flagship 9 kilometer model. And a lot of other groups around the world have found this as well. The forecast skill just isn't there. Claims about kilometer scale being needed for MJO, they haven't panned out. We actually get a pretty good MJO for climate simulation at 50 kilometers. The key is not resolution. Resolution helps you with forecasts. The key is having a coupled ocean of some sort. That's a pretty amazing finding over the last decade, is that the MJO really is a fundamentally coupled process. It's not really just resolution that gets it for you. And now the climate models do have good MJOs. So that's a bit of a cautionary thing. Is I think kilometer scale is great. I think there's a lot of great advantages to it. I want to be really careful about overselling it and saying this is going to be the key to solving, to improving our large scale climate and eliminating biases. I mean, it's going to take a lot of work to get to that point to realize the full potential of kilometer scale models. It won't be a gimme. The other thing I want to point out is that there's been a number of comparisons to CERN in particular in terms of what big colossal efforts can do. One thing to point out is here in the United States, we don't build huge colossal accelerators anymore. And a big part of that is that for many years, the funding for physics was mostly going into building these gigantic accelerators like the Tevatron, and wasn't going into things like solid state, which the particle physicists always disparaged as being squalid state. But here in America, there's been a big investment in condensed matter, solid state, material science. And I don't think it's hyperbolic to say that those are the technologies that are now saving the world. I mean, all of our climate technology is coming out of that investment in condensed matter, solid state, and material science. And a lot of those weren't these big, colossal, billion-dollar investments in many cases. I mean, now we've got people building out at scale as a result of the recent legislation, but a lot of it came from relatively smaller scale innovation, a relatively small focused group. And that's what I see right now in the kilometer scale modeling communities. We do have these relatively small, I mean, like, I don't know if you'd call 20 or 30 people small, but really that's where the innovation comes from. And indeed, once you have something, okay, go ahead and let's scale it up. Let's make it operational. And I think that'd be great. In fact, I think that'd be a great purpose for this computer. Is we've got a couple of very innovative efforts at kilometer scale. Let's make a computer that can run these people's models. I mean, like the idea yesterday of, basically the new computer, you put in a benchmark requirement. People bring their own models. They can work with the folks here at NCSA, the fantastic software engineers and hardware engineers, to help optimize those models and to help get the data to the users, to build an information system out of all this. So that's my 2 cents. And I understand some of it might be a little controversial and indeed contradictory to what other people said, but I strongly believe that basically is forcing everything into one basket, kind of like what CERN has done, may not be a very valuable thing.
Can I answer that point?
Yeah.
Could I answer that point? Sorry to interrupt, but I just if I can just spend a minute, because I worked for many years at the European Centre ECMWF, and I can't tell you how many program managers from the US, either NSF or NOAA, NASA, DOE, whatever, came through and asked me, well, they asked, I'm sure they asked lots of people, but they asked me in particular, what did I think the secret of ECMWF success was? And I said, it's pretty simple, really. We're an international organization, so we draw the best human resource talent from around many countries in Europe, and these countries pool also financial resources, so we can have some of the best infrastructure for doing research. And ECMWF, well, it has been pretty much since the day it started. It has been producing the most skillful weather forecasts, and the AI community now uses ECMWF as the sort of benchmark for beating. So I would say that is an example of where international collaboration has worked over and above the national Met services, and it's innovated a number of techniques like 4D VAR and so on, which probably wouldn't have happened in the national Met services. So I just feel I've experienced an example where international collaboration really has worked well, fantastically well. Thank you.
Oh, I think the European Center is a fantastic organization and a great example of what people can do by accomplishing things. One thing to keep in mind is that all those same countries that contribute to the European Center, a lot of them are also developing their own global weather prediction models.
I think Jim was gonna.
Yeah, I just wanted to quickly say, and thank you for your comments. I don't think there's any debate. I'd be surprised if there's debate in this room that this isn't a silver bullet. You just don't go to kilometer scale resolution and you don't encounter some of the problems. The same thing's true in model development. There's a lot of, even at the CMIP scale models right now, a lot of effort goes into improving each one of the components, and you put them all together and you have new challenges to settle. That's just the nature, that's the challenge of this. But to get to that kilometer scale, going back to some of the comments that Tim just made, in my view, that is the way forward to ultimately reducing some of these systematic biases that have plagued the models for generations and generations. I think we've all seen the plots. If you look at the so-called skill of CMIP 6 relative to CMIP 5, not a big change, right? And so, I think we understand enough about the system, resolving some of the mesoscale features can be very critical for this kind of upscaling. Andy can speak to this better than I can because he gave me the plot, but he gave me a plot that I showed recently, and in Tim's presentation talked about biases and blocking over the North Atlantic.
Sure.
And there's evidence that bias arises in the ECMWF forecasting system when, from the lack of resolving mesoscale convective outbreaks upstream over the US, right? That's one way forward. And it's not just atmospheric processes, but it's coupled processes. Resolving the coupled phenomena, the upwelling along the coast of the currents and things like that, don't only improve the climate simulations locally, but they can have remote impacts because of the upscaling. So it's not to say we run this and the biases are solved, but I think it's an essential step to start to ultimately solve those biases. It's really hard. It's going to take a lot of effort, but that's why it's exciting.
Did you want to say something? I just want to acknowledge Bill Putman. We're going to get to you, Bill. Just hang tight here. Go ahead.
Oh, I was just going to say, I don't believe it's true that the U.S. doesn't field billion-dollar projects anymore, and including how many billion was the exascale competing? $1.8 billion for the exascale competing project. but I don't believe that we're proposing here to suck all the money away from the climate community to do this thing. Rather, this is a different funding source, a different target for the effort. It's not to take the entire climate community and put it into kilometer scale. It's the foundation for building the next generation beyond. And my experience with astrophysics codes is it takes a while to tune a code up to have skill. So yeah, going to kilometer scale won't instantly overnight deliver skill. It's going to take us a number of years of work. I don't know how long, Ruby, you think that would be?
I'd just like to agree with the fact that these various centers around the world are doing, really good work. It's like a small company can be very agile compared to a really, really large company. And I think you're absolutely right. But I would point to NCAR as a great example of a consortium of universities that started in 1960 and has grown, and the whole purpose of NCAR was to establish a center that would allow the community to do things that individual academic institutions couldn't do. And that has worked exceptionally well. And now actually the reverse is sort of true as well. It's a very complementary thing in the sense of things like the social, behavioral, economic science dimensions of weather and climate. NCAR doesn't need to have a department of anthropology and political science and social science and so on, sociology. The universities have that and NCAR doesn't. So there's a symbiosis here that happens, I think, which has been really, really healthy for the community. And so I think that's an example of where you have the masses developing all these wonderful things that fed into creating the CSM and so on and so forth, but you needed a different kind of entity to manage that and to scale it up beyond what any given institution could do on its own. So I think it's a win-win. It's not a one or the other. It's an and both. And Jim, you can speak to that way better than I could. So Bill, I think you're up now. So feel free. And we we have Bill's video? Do we have the video that we could show the folks on Zoom that we could switch to them or?
It's fine.
Go ahead, Bill.
Hi, how are you? Sorry, it's tough to break in sometimes as a virtual attendee. I appreciate the opportunity. I wanted to say a couple of things. The first thing was that, no, skill is an interesting word, right? The question is how you measure skill, especially when you're thinking about kilometer scale models, right? Kilometer scale models can be, we've done a lot with kilometer scale models at NASA, and skill has been something that we measured with respect to our DA systems in NWP mode. Obviously, we don't do much in terms of long-term climate validation for skill from those particular resolutions. But we do develop a central model that can run across the scales, and that model evolves, with the single executable to run climate validation runs as well as NWP systems at higher resolution. So I think developing a single model across scales is a very important thing in terms of improving skill in general. We've shown that skill can be, kilometer scale models can be very skillful if they're developed in a scale aware sense, is what I would say. And then I have two other comments. The second one is we talk a lot about horizontal resolution in this meeting, and I think vertical resolution doesn't get enough play. It's been discussed briefly, but I think vertical resolution is key for many climate scale processes and the teleconnections, particularly when you talk about QBO, MGO connections. We have a system that's running now at 181 vertical levels, getting sub 500 meters just above the tropopause. That system is producing MJO in an uncoupled simulation where we're working on a paper on that. That's got a very, very strong QBO tuning that is contributing to that MGO connection. So I think vertical resolution plays much more of a role in those processes than horizontal resolution does. This is a 1 degree model with 181 vertical levels. The last piece I have to say is the discussion about observations, the use of observations, reanalysis, and data assimilation. I think that needs much more discussion in this context, right? It'll help in terms of validating models. It'll help in terms of, providing a resource for the developers and the climate developers at those scales to help us understand successes and failures in terms of skill in particular. So, and I guess that's a question that I have as a center that produces reanalyses for the United States. what kind of resolution are you looking for in terms of reanalysis? And is there enough information from the DA side to produce something that's valuable at those kind of resolutions for data simulation? So, I mean, those are my main comments so far, based on what I've seen from the meeting.
Anybody have a response to that? Okay. Yeah, one thing that just I think about training machine learning models, and of course they're being trained off of reanalysis data. And to Bill's point, if we could get finer scale real analysis data, would that improve somewhat substantially machine learning models? I don't know, but I'm assuming it would. And I know Tim, of course, commented, and he maybe mentioned this as much as I've seen him mention it in the past, but that is the upscale cascade of errors in machine learning models versus that in physics. I think he did talk about that in physics-based models. It's quite different. And so I don't know if Tim is still on, and we can go back to that. So anyway, go ahead, Michael.
So Kelvin, I'd like to take a step back and reflect on what are climate models actually for? Why do we do this? And I think that the principal reason is to help us understand the climate system and how it's changing. And so that would be something I would lead with in trying to promote this, is that for reasons that Jim and Dave and Tim have said, and the details are in the weeds which some of us know and love, about how we believe that kilometer scale is going to increase our understanding of the climate system. And so I think, to me, that's where you start. But we also have to recognize that climate models, which were originally intended to do that, have many other uses. And to the stakeholders, they have a different view of what a climate model is for. And I'm not sure we want to prioritize that, but I think we should recognize that there are multiple uses for climate, or reasons for climate models to exist, and they're all important in different ways. And we believe that this kind of advance is going to increase the utility of these models. And so, we love to get caught up in the details, and I'm very guilty of that myself. But I think trying to verbalize the big picture, I think, is useful in trying to promote this idea to people that may not appreciate these things. Thank you.
That's a great point, and I think also the use cases can really help with that of saying, everybody sees climate models and they're used in a different way, but we really do need to capture that. That's a really excellent point, because everyone's going to see it differently. Yeah. Thank you for that.
I think if I can just follow on from Mike's point, I think that one of the key things, of course, is that current climate models don't capture extreme weather. And I think you can relate that to economic impacts. So I know that last year, for the first time, for example, more than half of the billion-dollar disasters around the world, the insurance costs, right, were from convective storms. And that's something we cannot resolve, and we cannot say anything really about what's going to happen to with warming. And there's a number of other types of extreme weather events I think we struggle at as well, like the storms that we've seen in Central Europe, caused by blocking. We don't we don't produce the persistence of blocking that we need to produce in climate models to actually produce those types of events, yet they're happening in the real world, and we don't know. They appear to be increasing in frequency, I would say. We can't show that statistically, but we also, we can't simulate those adequately in climate models. And I think going to kilometer scales, we know already from the science we've done at the regional model scales with convection permitting models that we can actually start to certainly simulate these small scale processes like convective storms, supercells, hail and lightning, these types of things, wind gusts as well, that actually matter for society and impact. But I mean, as Tim was saying, and others have said as well, this feedback from those small scales could also improve those larger scale things, extremes as well, that matter. So I think for me, I would be hanging it off that economic cost as well, because it's costing society a lot actually, and we really don't know how these events are going to unfold in the future.
One of the things that we've always been challenged with at the storm scale is precipitation. And I think Tapio, the paper that he and co-authors wrote a few years ago about, the resolution and so on, talked a lot about that. And that really is a challenge. And there are a multiplicity of all kinds of microphysical schemes that we use at kilometer or below. George Bryan's looked at this, and getting the quantitative QPF, the quantitative precipitation forecasting right in these events in terms of the stuff that Francine is talking about and stakeholders is going to be a real challenge. And I think this could really accelerate that development. I think of all the science that can happen out of these kilometer scale models, it's breathtaking. I don't think we can really wrap our minds around that, but that is an area I think that is really going to receive a lot of attention, and already has been with things like dual pole data, radar data assimilation and so on. But I think that's a really critical area. We've got to get the precip right, and the types of precip and so on. And we still struggle with that at the weather scales with NWP models. So go ahead, and then we'll switch over to Bjorn. He's got his hand up.
I thought I'd just sort of summarize some of the things that have been said and try and bring them together a little bit, because they all do wrap together basically. So, we have systematic biases in current climate models and NWP models, but particularly current climate models, which are quite hard to tackle essentially. And as Dave pointed out, and Tim, there's evidence that as you do explicit convection on the grid scale, you can get the scale interactions and begin to resolve some in processes that we don't parameterize very well and they're quite hard to capture. So there is some kind of step change in going to have your convection and processes like that on the grid done by the dynamics. So not having deep convection parameterized is kind of a key part of that, and then having some grid scales that make sense are key to that. What that is a research question, and the opportunity to be able to do that research requires us to be able to have those kind of scales. And yes, as Bjorn said, so we probably want to be able to run at 200 meters for a short period of time, because that is the scale that begins to resolve the convective clouds, as we've shown. And we probably do want to be able to say, there's nothing magical about 1, but it's a nice round number. If you look at NWP systems, they all have like one, the Met Office had 1.5 for their regional model. It's a pragmatic decision in the end for the problem that you're trying to solve, but you've done a little bit of research to work out where the sweet spots are, and so you're going to want to do that. And it's probably less than 4, because people get a bit nervous about doing explicit convection at grid lengths longer than 4 kilometers. Mm-hmm. So we want the capability and the compute to be able to go down to a high resolution for short runs and kilometer kind of scales for much more longer runs, because we need the long runs to then see whether we're tackling any of these long-standing climate problems. So I think I'm not saying anything new there. I've just wrapped together everything everybody else has said.
Bjorn, did you still have your hand up?
I did. I was just gonna, do you hear me?
Yep, go ahead.
Yeah, I can put my video on. I don't know if that matters, but I was just gonna bring in another point, which is, you've mentioned it several times, Kelvin, and I think it's worth bringing up again. And that is, how do we communicate the importance of the problem and the ambition and the potential of the science if we don't reach for the stars, so to speak? So when you think of society as a whole, and on one hand, the science community is saying, this is a hugely urgent problem that, is threatening societies and our existence on the planet, but it's not really worth using even the existing computers that we have to their fullest to try to find out a little bit more about it. I mean, that's a sort of dissonance that comes across, which I think is counterproductive. It's counterproductive for the social debate, but it's also counterproductive for attracting the best minds to the field. So being able to articulate an ambition, and I think we have a great ambition here in terms of what we could do, I think is a lot of collateral benefit, both in terms of invigorating our science as a whole, in terms of raising the stakes in the social discussion about climate change. And on the computing ambition, I would just ask, maybe in the US it's different, but we did a survey of Euro HPC, and so we're all kind of a factor of 2 down. So we have Leonardo and Mare Nostra and Lumi, and they're sort of 300 to 500 petaflop machines. And the fraction of those machines' time, which is used for climate, is about 2%. And it's almost all through our institute. So how can that be? And how could we not want to even use the existing machines to their fullest, let alone build better machines, which are more ecological and adapted to the purposes that we're exploring? And I think that's also a technological adventure, which makes it projects our field much more broadly in the scientific community, because suddenly we become the driver and the innovator for new information technologies. And so I think we should also keep this broader context in mind, and we shouldn't quibble about, some of the things we sometimes quibble about in the way families quibble about little things, but unite around big things. So I hope you guys have a lot of success in the rest of the day in reaching out to the big picture.
Great, thank you.
Oh, no, I was just trying to figure out how much time is on Frontier, and I was gonna have Jim check with Oak Ridge and see how much time is on the climate.
Yeah,
on Frontier.
I'm sure NERSC gets about between 20 to 25% typically.
I mean, material science has most.
Yeah, they have most of the material scientists get a third of the machine.
But if I was sitting here and thinking, if you compare, if you're talking about CERN, okay, CERN is a big experiment to find the smallest particle in the world. Well, you can't do that with climate. You can't go out and run an experiment. You can, you can see clouds and look at things. Your big machine to study climate is a computer. So you have to, so it makes sense to come up with a machine that can do what you need to do, much like they do at CERN.
Yeah. And, I of course have ambition to change, push roadmaps and have build a better machine from the ground up, but it can also be used, this analysis of what it requires to do a kilometer scale model to select a better machine, because we're not selecting the current machines that we have selected, or we're not selected based on the climate model requirements, and it's reflected in the performance we see.
Well, and I want to go back to what other people have said. I've had to justify a program. So I think one of the important things that can come out of today is that elevator speech that the senator or the philanthropist will understand. You've got 2 minutes in an elevator to tell them, and I'm sorry, adding the mesoscale or adding vertical isn't going to work for these guys. You have to say, why does my district care? And I think if you can come out with that pithy, why this is transformational to those people, I think you'll have had, be as successful as doing your 1 kilometer.
So could we talk just a little bit then about the computational environment? Because I think at the end of the day, that's sort of what hangs us up a little bit in terms of a community of doing the really transformative things we want to do. I mean, MPI, as we heard, is getting down to 200 meters globally, which is just amazing for short periods of time. But you can learn a lot from short periods of time. But if we want to do these multi-decadal runs and so on, and have large ensembles and all kinds of other experiments, it seems likely that we're going to need something beyond what we already have. Though I agree with Bjorn that we need to always make sure we're using what we have, and that's part of the argument, I think, to philanthropists or whatever. What are you doing with what you already have? But the compelling situation is we get to a kilometer and we can do all these other things, not build from the ground up a new thing or fabricate new chips or whatever. It would be, can we add capability to something that already exists or is in the near future to really make these models sing? And again, we're not innovating completely new hardware and chips and things like that, but there could be some really interesting spillover effects in a very aggressive approach, as Cliff was saying, that, really full on, go for it, do some things. There's a lot of things that would come out of that other than just the endpoint of a new capability for computational climate modeling. But what would that look like? What is needed to take the performance to a new level Again, not talking about building a brand new system from the ground up, but latching onto something that exists or whatever. John, you've done a lot of analysis. We know that climate models are compute hungry. We know that we're not getting nearly the performance out of existing systems that we need to. So what's the answer there? What would unlock the potential of what we're trying to achieve and allow us to, as a global community, do that kind of really extraordinary push forward?
Yeah, so I mean, we're in the middle of our analysis. Laura's just getting some good results out now. Like I said, we're not going to engineer a system in this meeting here, but we can, over the next few months, I'm hoping to put some interesting ideas on the table that would range from augmentation of existing designs to all the way to let's rearrange the chiplets to build the machine that we really want. We need to do an alternatives analysis, but you have to have a model for what the outcome would be in order to vet those alternatives. So I'm not going to, there are a lot of great alternatives that are on the table, and we haven't down selected from them. There's these 3D caches that are coming online where we could fit the entire model onto the chip. And then memory bandwidth no longer is an issue. There may be other issues that come up, but that's part of the vetting process. Is let's put that alternative on the table and let's let it play out with our performance model. The other things are more ambitious things using the ARM ecosystem, which allows you to mix and match the pieces that you need and co-integrate them. That would be the more aggressive solution. And it's yeah.
No,
So
I was just going to say, it seems to me if we could ever get the CHIPS Act funded, a lot of that, and I think even a lot with that and legislation I've seen, has the option for prototypes. And this is exactly what you want to do, is develop a couple of prototypes to try some things.
Yeah. Yeah, and so we have to there's a lot of really cool ideas that the computer architects in this audience have brought forward. And I think that we use the model to select it down to a couple of really good ideas that we can virtually prototype using FPGAs to simulate these machines before you build them. But ultimately with the CHIPS Act funding, and there's also an EU CHIPS Act, get a couple of prototypes to show that this could really work. And when you get to the prototype level, we could really run the actual code, the actual climate codes on these things, and really make a transformational change. I think that anyways, it starts though with the model so that we can vet the outcomes before we actually sink $1 billion into a system. And we know how to do these steps towards understanding what's going to work before we invest the big dollars to scale that up.
And I'd like to add a little bit to that. And that is that what I hear in some of the conversation is going to kilometer scale has both a scientific argument, but also a technology argument. And what I want the scientists in the group to do is not think about the technological constraints. Okay, so for many decades, I've worked with lots of researchers in many fields. And when I'm having a discussion with them about trying to support their needs, what I always ask them is to tell me the problem you want to solve. Don't tell me how you want to solve it. Okay? Because we're limiting what we think we can do by what we think the technology can support. And as John just explained, there are many options out there that we may not all be aware of. Let the bring the technology side of it. Give us that as a problem to solve. Don't assume the solution. And so then the question about kilometer scale is not a technology discussion. It's what's the scientific merit of doing that? Does it produce the results that we need to inform the practitioners that we're trying to support?
Yeah,
that's what should drive what happens, and let the technologists take those as requirements and then come with the solutions. Because I think there are even additional solutions than what John has been talking about. They're a bit more speculative, but they're emerging technologies that really could come to bear on these things. So don't constrain your thinking of what is possible and what really needs to be done by whether you think the technology will be there or not.
I'll even have a case in point with the exascale program. In 2009, we said, oh, we have to have these 3D stacked memories or else we're not going to hit our goals. And we talked to the vendors and they're like, yeah, we have no interest in that. That's crazy, crazy stuff. And then by the time 2016 rolled around, all the GPU vendors were running with HBM stacks because the alternatives were so far worse. So don't presuppose how technology roadmaps are going to unfurl. We knew about HBMs, we knew about GPUs in 2009. We said, there's no way that's going to work. And then that's what we ultimately fielded.
Well, if you go back further, I believe you were a naysayer when it came to using GPUs
I
with
was,
CPUs.
and I've learned my lesson. So presupposing technology roadmaps were going to look like what you've done up till now is not. You have to be open-minded and you have to come up with a framework to vet the alternatives and not say this isn't going to work just because it didn't work before.
But isn't it also true that you have to make sure, and to John's point, John Town's point about you tell me what you need, but to make sure that it's not just a one-way thing, but there's an interactive conversation going on with the people that are developing it, to where it's like, I'm not just giving you my needs, we're dialoguing about this and we're part of the process. We're not just, hey, here's the thing, and they go away and 2 years later come back,
And
right?
that's what the vendors want.
That's what the vendors want.
Because they see that that's what eventually they might be able to use this as a product down the line.
Right.
They need that communication, but they need to know what your bottlenecks are.
Mm-hmm.
Yeah, and not every bottleneck is going to be, it's really amazing to me talking with the vendors that there's some things that the community thinks is hard that turn out to be easy because there's economic force behind it. And there's some things that sound really easy, but they turn out to be really hard. And that's why it's a two-way conversation, is that the feedback you get from the vendor also includes market forces, which is something that we as scientists do not understand, and nor should we.
Go ahead.
I think we all agree that achieving a step change in A, the accuracy of climate models, and B, their usability for stakeholders is important. And they're somewhat separate problems. I think the making climate information useful and accessible, that's probably the lowest hanging fruit, where relatively quickly a lot of progress could be made. But let me focus on the accuracy of climate modeling, and just want to build on things Lucas and Bill and a few others people said. And in response to what Tim says, the alleged evidence that going to kilometer scales leads to step change, that evidence isn't there. We have atmospheric turbulence spectra. They have no step anywhere. They continue down K to minus 5/3 spectrum down to millimeter scales. So models are now nowhere near converged at a kilometer, but there is plenty of room at the bottom. Of course, we should press resolution as far as we can. There's benefits from increased resolution at every scale, kilometer and beyond, and we should press the frontier as much as we can. But where do we achieve a step change? I think just resolution alone is not going to do it. Again, it can be quantified based on the spectra. You can look at the vertical kinetic energy spectrum in the atmosphere. You can quantify the benefit of resolution. It is less than the square root in terms of kinetic energy, marginal kinetic energy resolved per resolution, whereas the compute cost scales cubically. So for a factor 10 more resolution.
Square.
Well, there's a time step, right?
That's what I'm talking about. The time step is.
So right now it scales cubically. Hypothetically, maybe you can get around it, but right now, for all practical purposes, it's cubic. So a factor 10 in resolution is a factor 1,000 in compute, is a factor 2.5 in benefit in vertical kinetic energy. So that's a worse scaling law than the AI scaling laws we're talking about, where scale is also helping, right? It's a massive debate, where increasingly debate goes towards we need to think about smaller models as well and what we can do with them. So resolution alone, I don't think will do it, but I think a step change is feasible and it's achievable. And we heard a lot about the potential of AI, but I'm not really talking about that here. And I think what you need is an all of the above approach. You need whatever resolution you can get. You need to build models. And if we talk about co-design, we should talk about co-design, how to implement AI tools inside models effectively. I think that's absolutely critical for progress. And I think there's also plenty of room in basic science progress, how we design parameterizations that they're ready for learning from data and the like. And I think we can achieve a step change, but it's probably an all of the above approach and not just brute force computing. In fact, the discussion so far strikes me as very much business as usual. We are talking about accelerating business as usual by a bit, right? We'll reach kilometer scale resolution at some point, and we maybe can move this forward by a little bit. But it's very much how we have always done things. It doesn't strike me as transformative.
Thanks, Tapio. I think if you look at all of what led up to this, all the pre-summit intensive, we are doing all of the above. AI is totally integrated in this. It's not a hang on the side. It's completely integrated in the models, outside of the models, with the data, all that kind of stuff. You're right. It's not about resolution alone. There's a lot of research that has to happen. So I think you bring up an extremely important point, but I assure you haven't ignored it. It's totally there. It is completely there. George Bryan, are you still here? George has done a lot of work going into models down at 50 meters, whatever, looking at the turbulence spectra. And Tapio brings up a very good point that we're not even in the inertial subrange at half a kilometer or even 200-300 meters. But from a practical point of view in weather forecasting, we've looked at this deeply. It doesn't mean that if you're not in the inertial subrange, there's no value to the forecast. So it's a question of value versus accuracy versus fidelity in terms of the turbulence spectra. And all three are important, but at the end of the day, it's about what can you deliver in terms of the value of a practical forecast. Even though you're not in the inertial subrange, you're still doing a lot better than you are at 25 kilometers. So these are the key questions we have to confront. But I think we have to be careful not to say because it's not doing something, therefore it's not valuable. The value proposition is a very, very different thing. And so we just have to always be mindful of that. So those are very good points. Sorry.
Could I come back to that point?
Oh, sorry. Yeah, Tim, go ahead. Sorry, I didn't see.
I mean, I just wonder if I could address Tapio's point. For example, in my talk, I acknowledged the existence of these power laws. And for me, it makes the concept of parameterization as a deterministic process questionable. So that's why I was proposing that we should, and I very strongly believe if we go to kilometer scale models, our parameterizations must be stochastic to represent the fact that we don't have this simple, we do have a power law structure. We don't have a simple sort of spectrum that just goes to zero with a little bump at the subgrid scale. But I just want to say to Tapio that, if you wanted to change the large scale climate of a model as much as you possibly could with a small tweak to one of the many parameters in the parameterizations, all the evidence is that the parameter that you would change would be something in the deep convection, and typically things like the entrainment parameter. I remember years ago, Miles Allen, a colleague of mine at Oxford, with his team, tweaked the Met Office convective entrainment parameter by some small amount, I can't remember which, and the climate sensitivity went to 15 degrees Celsius, 15 degrees from whatever it is we think it is now, 2 or 3 degrees. So it's telling us that if there is a single process that would be better represented with the proper laws of physics rather than these parameterizations, it would be convection. And that's one of the key reasons why we want to at least start to resolve this process. Of course, as I say, we'll need stochastic schemes to represent the power law. I would say that the NWP community has actually been pretty progressive in terms of improving the resolution of the models. The ECMWF ensemble now is at 9 kilometers. And that's because we've seen very clearly the improvement that improved resolution brings. But I would say the climate community has been much slower in this respect. And of course, they've got other things to worry about, like Earth system complexity. But to say that you know, the 1 kilometer goal is just business as usual for the climate community. I don't think that's right at all. We're trying to stress the importance of resolution that has been so important for NWP at the forefront. And I think that is a game changer. So I don't agree entirely with Tapio's comment.
Okay, let me just say, and just something quick in response. I agree with pretty much everything you said there. And just to be clear, I think we should press resolution as far as we can because it helps resolve convection and all of that. But your criticism is of prioritizations that are 50 years old or so that we use in models, or diagnostic functions of the state of the atmosphere with which you try to describe convection and the like. I completely agree. This is an inadequate concept once you reach resolutions of 10 kilometers already. You do need stochastic terms, completely agree. Not only that, you need memory terms, you need prognostic equations for prioritizations. There's no time scale or space scale separation anymore. You need both, absolutely. And part of my point is, let's think what we need and how we can use machine learning within a reasonable physically informed framework, right? Moritz-Zwanzig formalism tells us you need memory, you need stochastic terms. Let's include them and then think about how we can use machine learning in that framework in the most effective way to do better. All the while by pressing the resolution as far as we can, right?
Yep.
I'm not against that.
Yep. Good point. Go ahead. We'll go ahead.
So I agree. And then I think that turns into when we're looking at architectures or what we can achieve with certain architectures, we need to include those embedded AI models in physics models as part of the analysis.
Absolutely. Yep, for sure. Yeah.
Two maybe optimistic observations. One, building on where John is from talking to the other architects in the room, feels to me like you're within striking distance, being able to build machines that are highly likely to work to correctly compute at the scale you want, the kinds of things you want. This goes back to John T's separation of science versus technology. Is the science right? And tags back to Tapio's concern about, like, did we get, say, the math right? The other optimistic point I wanted to make was the Anton project re-engineered in a radical way, co-design, everything, numerics, parallelization, algorithms, and so forth. And that re-examination showed us things that were broken in the previous scientific consensus that nobody had seen before. Anton machines are parallel invariant regardless of node count. They compute exactly the same thing. They're deterministic. In certain cases, they're reversible. That allowed us to see failures in the energy drift terms that nobody else using floating point had seen. So I think another possible reason to embark on this journey is because of the feedback loop to the problems that, where's Tapio? Tapio mentioned that the business as usual approach is hiding biases. And by coming up with something which is not necessarily business as usual, you might actually do better science. It'll be painful. You'll be programming in nasty languages at low level bitwise and so forth. It'll require digging into the bugs. It'll be like, what do you mean my energy drift went negative? What's refrigerating? Which, you know, something that shouldn't be in the simulation. But those mini quests will tell you more about the actual science you're trying to do and push you places that, I don't know if they'll be publishable, but they'll be effective in the scientific quest that you're on.
Thanks, Cliff.
We have used the word like a stakeholder a lot. Yeah. I try to think maybe we phrase it a little bit differently. You know, what about we think about as a consumer? Yeah. As a consumer, for example, I go to the department store, I just buy the clothes that fits me. If somebody at the department store, I have the best quality stack of fabric. Yeah, maybe, but that's not what I'm buying because I cannot use it directly yet. Now, if with that kind of concept, you would think, if we look at the consumer, what are the consumer consumption of the weather informations? Yeah, I would argue that most of those are beyond kilometer scale climate model, right? It's beyond. Now, scientifically, it is not trying to say that to downplay the significance, the meaningfulness of the project of a kilometer scale in the global climate model, but probably we need to go beyond that. Yeah, and then what is my pitch deck? How are we going to sell this thing to people and saying that what we are doing is really going to impact you a lot. Yeah, people really see it. People can use it. So almost like a fashion, right? A department store, they don't show a stack of fabric, and they show the most beautiful clothes, and then right, and then yeah. So that's actually the concept. That what I'm thinking is that difficult to from kilometer scale and downscaling and to the point where actually consumer, that's exactly what I'm going to buy and use. Is that a low-hanging fruit? Yeah, and should that be part of the emphasis, right? Yeah. Until we get to the point to show people a beautiful and useful, adequate, and perfectly fit in clothes, we just don't get there, I think. And people are not going to pay. Yeah, that's what.
Yeah, no, good point. And I was just talking about this with somebody in terms of the UK Met Office. Their new computer is like a $1.2 billion procurement. And they were making the argument and actually had a very, very prestigious organization do a cost analysis and do a benefit analysis also. He said, well, you know, we're going to save the UK this much money by having this new computer and so on. And at least here in America, it's very difficult to convince, say, Congress, for example, that we're going to, you know, we need this because we're going to prevent something from happening. That's very hard. What the UK did, though, what UK Met did, they said, we're going to turn this not just in terms of what we're preventing in terms of loss, but what we're going to do in terms of building the economy and creating wealth. That was what pushed it over the top. And that I thought was fascinating. And in fact, it's the right approach, right? If we're gonna build stuff, not just prevent bad stuff from happening, not in terms of weather, but we're gonna prevent loss. We're gonna actually build gain, and that tends to resonate much more. Yeah, that was very interesting. Go ahead.
Yeah, so wanted to first of all just start off by echoing what Cliff said, that I think we can definitely build computer systems that can solve the problems that you're all trying to solve. I think it's going to be very important to look at it holistically to make sure that we're building something that's extremely useful, both for the scientists, but then also the practitioners that want to be able to take the data off of the machine. And then another key thing is that so far there's been a lot of really good discussions about, like, for example, coupling the physics and the AI models. But I would encourage everybody to think more broadly about how this big trend in AI can be useful in the computer system design and also in your own science. So just as examples, there's real opportunities for using AI to do code optimization and code translation to be able to run on new architectures. There's also real opportunities to be able to use it to help with prototyping and performance estimation and evaluation. So I think as we think about, you know, this new endeavor, really leveraging things that are happening in the AI space as well as the HPC space can be very valuable in achieving the overall goals and making sure that we achieve those goals as quickly as possible.
Yeah. And just for credibility, Mike Schulte from AMD, so speaks from me.
Very well said, yeah.
So Kelvin, since we're talking about technology, I'd like to go for something for Barb and John, back to an idea that labeled John and I as a bunch of radicals from Berkeley. And I can remember in the 2008 summit, the guy from Cray having me for lunch on this. But the thought is that building a special purpose machine for climate is maybe an idea that could be extensible to other areas for high performance computing. And for the Department of Energy, we thought, I think there were 5 major users of cycles at NERSC and the other computer centers. And I can't remember all of them. I think it was material science, cosmology, quantum chromodynamics, and something else. And now you could add machine learning to that. And so what we thought as the radical idea was that maybe we shouldn't be building general purpose machines any longer. Maybe Frontier should be the last $200 million machine we buy. And that instead to have the major consumers of cycles have each one have their own special purpose machine. And so what would work well for climate wouldn't work well for material science, but give them their own machine. Users would be much happier because they would have fewer people to compete with and their code would be a lot faster. And so, so John, I mean, maybe you can elaborate on this and how Green Flash may have actually informed some architecture design, if it did at all. Please be kinder than the guy from Cray was.
Well, I could say at the time I was also CTO for NERSC, and internal, when you're operating a center that's responsible for all of the science and DOE, you don't want to be in the middle of a conversation about whose science is better. So, so I understood where the facilities were coming from, and I don't think it has to be either or. I think that there are problems that are important enough that you create that microscope or that time machine, as Cliff said, that focuses on solving the problem. And it comes back again to it's about solving the problem. And if you look and say that business as usual isn't going to solve this problem, like John Towns was saying, we gather the requirements and don't worry about technological limitations that you imagine in your mind. You've got to solve that problem, right? But that doesn't have to be an either or, that everything gets disaggregated into topical systems, but there may be some topics that are important enough that you should build a system for it. And I know that HEP, the instrumentation that they build in addition to their bespoke detectors, is because Sony ain't going to supply a 200,000 frame per second detector for you. It's just not going to happen. But if the problem is important enough, and that goes back to what was said earlier, that this problem is important enough that it deserves this kind of focus.
So to follow up a little on that, for Kelvin's benefit, I think that there's not just, we're not just talking about doing better climate here. We're talking about doing more efficient computing, and that there are potential spin-offs to other disciplines that are important.
Right.
And so, that's, maybe not the prime selling point, but it is also, I think, a point that should be noted and might generate a little bit of interest.
Where did the IBM Blue Gene come from?
Yeah, no, the IBM Blue Gene came from saying that the chemistry and material science problems were important enough.
LQCD?
LQCD, well, right, so that's right, that was a spinoff, yes. It started as a QCD machine and just determined that actually the same characteristics were beneficial for material science problems. Nope.
but I think it's true that it is, for those of us that look at a lot of different classes of applications in different domains, what is the bottleneck here in these sorts of models is the same bottleneck to varying degrees for other application classes. And so there's a benefit here. It's not just about a benefit for these climate codes. There are many applications that would benefit from some of the architectural changes that would really make climate codes run better. So there is a broader impact there. I mean, what we face with many of the vendors face with respect to commodity PCs and things like that, because the technology is fundamental, right? So they don't get the scale of that. But if we can make the argument that there would be a benefit beyond just this domain, we have at least something to go to and talk to the produce these things.
And it's also the case that the market is actually changing very rapidly with the Moore's law kind of moderating. I mean, it's not dead, but moderating. The part of the market that has all the economic force right now is actually the hyperscalers. They're consuming about half all the server class equipment out there, and they're discovering that they're creating their own chips. They're actually specializing for targeted pieces of their workload. Google TPU. So Cliff here is involved in designing that is a full custom hardware design for very important parts of their workload. And so this is happening. This is happening broadly in the marketplace, and the market is in the process of retooling to go from just fully general purpose everywhere to being agile and flexible to target high value markets. So that flexibility is something that we can also tap into, and it's evolving very quickly.
So I was talking to Chris Dobbins about this. What are the forcing functions out there now for, you talk about, this agility and so on. Are there It sounds to me like there's just a multiplicity of forcing functions, right? There, it used to be, you know, the days of Cray and thinking machines and so on. There, you know, but things change, right? It's transaction processing, online shopping, streaming video, and now, you know, gaming certainly was huge. Is it now there's just a whole big universe of stuff, and companies are saying, look, we've got to accommodate all that, so we got to be really flexible. Has that resulted in lack of doing, you know, like you have a scanner that goes over a broad range, you're not really getting any of the channels well. If you get a much narrow range, you're getting those really well. Does that compromise anything in terms of a capability by trying to address so many users, or is it actually driving in the opposite direction of improving the capability for those multiplicity of users? What are the drivers out there?
I think, well, you go back to the vendors that sorry, vendors, but as we built exascale, even as we started down the petascale route, we had to deal with commodity chips.
Yeah.
They were not designing the chips for what we needed.
Right.
So we had to, and we had to work with the vendors to add some functionalities that we needed. So I think right now, like John said, it's the cloud providers that are really driving what we need to do. So if you can get the cloud vendors interested in this, you've got.
So with that, would you say cloud includes AI?
Oh, yes. Oh, yes.
I mean, that's really where it is, right? Yeah. It's not just in the frontier systems, AI, but it's.
Look, training these large models is a huge memory bandwidth and IO constrained operation. Same problem.
Yeah, same problem. Yeah. Maria, go ahead.
Hello. I feel like we all are agreeing on the scientific value of this effort. And perhaps we don't know exactly how we will go about the hardware or where AI fits and these sorts of questions. And I think some scientific disagreement is healthy, right? So I think my general question is, what does success look like for this summit? Is it us all agreeing on a scientific effort or on the scientific approach? Because I think that won't happen, and that's, again, healthy and good. Should we discuss how we should get organized as a community if we really want to facilitate this international collaboration? What are the roles? What does this look like? Or yeah, I guess I'm trying to think beyond the specific details, since we really won't hash that out in this meeting.
Yeah. So I think as we talked this morning, the planning committee said, look, you were kind of three things. One would be the science, you know, what are the goals of advantages, kilometer scale? Do we agree on that? And clearly, I think there's agreement. Second thing is the computational piece. The third piece we haven't begun to talk about yet is how do we get there, right? I mean, if we are talking about doing something, you know, grand, we're probably not going to, I would say we're not going to go to government funding agencies, at least not initially. We're going to go to some of the places we've been talking about in rather mysterious ways. And so what does that look like? And I think the only way that that even comes close to making sense is by joining hands with the whole international community coming together as a whole. And again, this summit is just, we're just one of the members of the team, right? There's Destiny, there's Eve, there's all these other groups. We're just, you know, kind of bringing a little bit, shining a little bit brighter light on some other aspects of this thing and talking a little bit about the computational piece, because that's the piece that has sort of not been overlooked. It's recognized, but it hasn't really been discussed much. So the third piece I wanted to talk about today is what you just brought up. How do we do this? And, you know, in terms of what is needed in organizing more effectively than is happening now, the international community. And by that, I mean lots of things, but especially the groups that are developing these kilometer scale models to enhance the collaborative activities among them, to figure out how we could speak with somewhat of a single voice in looking to do something much bigger in terms of meeting the needs of the computational capabilities, and to also engaging the stakeholders in a more effective manner than we are now and defining what that even means. So that's the third piece of what to talk about. The science and the AI is there for sure. You know, that's happening. It's going to happen. That's not, you know, there are plenty of conferences to talk about that stuff. So the third piece that we haven't yet begun to talk about, we will, is exactly that last part.
Great. And I guess I just want to emphasize that I appreciate the sentiment in that as an international community holding hands and moving forward. And I think as scientists in this room, many people believe in that, right? And we know how important it is to collaborate and agree and disagree. But perhaps thinking about this more concretely, right? The planning committee has worked very hard on putting this effort together. You yourself have worked so hard, even obtaining the funding for this effort. And all the folks in this room have taken time off from their very busy schedules to be here because they care about this effort. And so how do we ensure that everyone is acknowledged and has a role to play? Because I think expecting everyone to sort of continue on this without defined roles and where they fit in this vision is really tough.
Yeah, no, that's the third piece. You've laid it out exactly as we want to talk about it, right? We don't want to just say, okay, everybody, thank you for coming. We've got to have some next steps. And that's on our agenda to talk about what are the next steps, very concrete steps. What do we do? How do we set this thing up? We had a breakout yesterday where we talked about how to organize the international community, how that might be done. Cliff was there, Jim was there. We reported that out, so we can come back to that as well. But I do want to leave here, especially in writing the NSF report, to say, what did we agree on and where do we go from here? That's really important. But on the other hand, let me be careful though, where we go from here isn't just our responsibility. There are folks that aren't here now that need to be part of the conversation, that they're not. We don't want to make it sound like, well, because you weren't here, too bad. We made a lot of decisions. So we got to be very, very careful how we do this, I think.
I agree with that, but the folks here did take time.
No, I understand, but we have to be sensitive. We have to be sensitive.
So I do want to talk a little bit about maybe where we want to go next. And it goes back to some of the discussions we've had before and that were touched upon today. We're trying to cover a lot of ground here, and it's very hard when you're trying to cover a lot of ground in a single meeting. And there are reasons you do it in terms of trying to have a picture of the entire vision and such. But as we discussed yesterday, in order to really solve problems, one of the really good ways of doing it is breaking down the problems into the constituent components. And the hierarchy we discussed, I think, was a really good way to do it. John Turner talked today about focusing on the use cases and requirements, which we had discussed yesterday. We had talked about how they're at different levels. So I'm going to set aside the international collaboration right now and focus on recommendations to how to progress how you do these things at each level. So, we have the client or end user use cases, which, we've had some good discussion about how those map to this data interpretation level, how, you then meet those use cases by providing the interpretations of the data to those end users. That's a focus area. Get a group together to just talk about that, where you have the end users talking to the data scientists who are going to do that work. You isolate that, you have that discussion. You can do that in isolation. Then the data scientists can understand what the computational requirements are, bring it to the computer scientists if they have to help design systems for that. The same thing happens with climate modeling, right? When you're talking about the actual climate modeling itself, whether it's just physics or doing AI and hybrid models, which I think we're all kind of headed towards, it's the same thing. What are the use cases and the requirements without going into the implementations, as John said, that those modelers are trying to solve and work with the computer scientists and the vendors directly on what can be done. And this is where the market forces will come into play. The vendors are going to push back and say, I can't spend time on that. Could you use this instead? But again, a focused discussion and a two-way discussion between those groups, and do that at every level. If we don't set that up, if we keep trying to do it all in one large group, progress to me is much harder.
Yeah, totally agree. Absolutely right. And these can be, bilateral discussions. They don't have to be multilateral. We get the key groups together and do that and coordinate that sort of thing. Right. Yeah. Go ahead.
So I think everybody, well, in general, there's agreement that this is a good thing to do and it's a needed thing to do and whatever. I don't know if we've talked enough about why is it the right time to make this investment or make this effort, right? And then there's a question about what if we wait 5 years or what if we wait 10 years? So somehow in the advocating for a bigger initiative, we have to be able to say why is now the right time. Maybe things have come together. Maybe it's the AI. Obviously, climate needs to be addressed in a quick manner. But I don't know why now versus why in 5 years or 10 years.
Yeah. Yeah, that's a great point. In fact, in the proposal to NSF, there was a whole section on that. Why, what happened several years ago, why now is the right time. And you're absolutely right. That has to really be front and center. Because I think there is a lot of why now is the right time to do this.
Repeat then what was in the proposal about why now?
Well, you look at the technological capabilities, number one, the scientific capabilities, the fact that these kilometer scale models are already being developed. We've learned a lot from the weather prediction community. I think there needs to be more coordination there. I think that's important. I think politically, I think many more people are supportive of the idea of understanding climate than they were even 5 years ago. I think that there's the need for where the community is as far as stakeholders and practitioners. They know the limits of what they're getting. They're not getting what they need. And they feel like, hey, we talk to various insurance companies and they tell us we can't just keep raising rates. There's got to be an alternative. And part of that alternative involves what we're talking about here. The hardware capabilities. The geopolitical climate is quite different right now. And that's a really important forcing function. Plus, most of all, as Francina keeps reminding us, the clock is ticking. It's 2024. And, there's an urgency to this fundamentally, whereas maybe 10 years ago, yeah, there was, but not like it is today. So I think there's a multiplicity of reasons, but that the point is exactly spot on, that we have to be very, very clear about that as to why we can't just wait. But I think we've advanced so much in the science and the understanding. There's a whole lot more needs to be done. But I think the stars are aligning in ways that they weren't even 5 years ago for us to really do something now. And I'd like to hear other thoughts here about that.
Can I just make the very elementary point that
please do.
that nature is changing. We've seen absolutely unprecedented
another point.
Extreme events, but every type of extreme event, from a heat wave to a drought to a storm to a flood, absolutely unprecedented. And the more these happen, the more we realize they're all outside the range of capability of our current models. So, the urgency is really to be able to keep up with nature, what nature is actually throwing at us. We've got to keep up with that, and we're not keeping up with it in our model predictions and projections. So the models are not able to simulate these emerging extremes. So that for me is the single biggest reason for treating this with extreme urgency.
Right. Yeah, we actually, we made that point. We said it's evident today, and that's actually what's, I think, changed a lot of people's opinions about this who were skeptical before. It's becoming very, very evident. Yeah, absolutely true, Tim. Thank you for that. Yeah, please.
Yeah, Christiane Jablonowski, University of Michigan. Yeah, I have about maybe 5 talking points here, so bear with me. I maybe want to just reiterate, I think we converge on the idea that kilometer scale is the way to go, but I don't think we converge on the idea how to get there. And I want to just add a couple of thoughts about that. Maybe one thing we should all, just from a numerical viewpoint, understand that even if we have grid spacings of 1 kilometer, we are not resolving the 1 kilometer scale. We are resolving the 6 to 8 or 10 kilometer scale. So I hope that's clear in this room. So even if we go after 2 or 3 kilometers, we just want to keep that in mind. But we would definitely be able with a 1, 2, 3 kilometer grid spacing to go after the mesoscale, and that was the understood topic, that this would be the crucial point. I just want to maybe get some ideas out, and Tapio, alluded to that we are not really so transformative right now in the way we think about our models. I think when we just do business as usual, we go finer and finer resolution. We can even maybe do this currently with at 3 kilometer time scale, 3 kilometer spatial scales. But I think why not maybe even think about a 10 kilometer type grid spacing with machine learning as a super resolution on top. That could be a post-processing step, or we could build it into the hybrid approach, build it into the modeling framework. These are, I guess, approaches we haven't really discussed or fleshed out in the community. It's a research question, but I personally, I see even potential with 10 kilometer modeling, I guess, coupled, we can probably do right now for 30, for 40, whatever years. But can we, bring in the machine learning, I guess, in a trustworthy way? That will be a talking point. Can we trust super resolution? And I think we saw these very convincing examples from Google on Monday, where we have, these ships, that all these movies were created, or the visuals were created with machine learning. Can we do this with our climate data, and can we ensure they are trustworthy? So verification will actually be a crucial point. And maybe we shouldn't reach for the sky right now. So sky would be, 30 years of high resolution climate modeling. We should probably think about stepping stones, and one should be maybe a sub-seasonal timescale or seasonal to sub-seasonal, talking about maybe multi-month to multi-year. And I think we could do this right now with even existing technology, even at 1 kilometer scale. We could probably do a year as a demonstration project and then explore the ideas whether machine learning could also get the same answer with 10 kilometers and machine learning as super resolution on top. I think we should be creative in the way we think about the problem. And I guess one more point, if you bear with me, Björn Stevens brought up that they can do 100 days per year. I think that's promising, but we didn't talk about ensembles. And I think one single deterministic model simulation actually doesn't get us anywhere in climate. So if we then think about maybe an ensemble of a 50 or 100 member ensemble, then this 100 days per year is down to 1. Yeah. So I think that's a good just talking point to keep in mind that ensembles should be in the picture.
Thank you. That's
a lot of
super
thoughts here.
Yeah, ensemble is very important, and I think the whole we've always talked about how many, what type. Tim was talking about the perturb models, the multi models, blah blah blah. All those important points, and then AI, this X factor of AI doing ensembles incredibly inexpensively and huge number. Big issue, and I think that was in the R&D agenda as well. So,
of course, AI we may view it as a hallucination, but maybe it's a useful, hallucination that actually does provide useful information for the stakeholders.
Right. Absolutely. Well, I think we've been at it now for about an hour and a half. So why don't we, if we could, take a break and let us kind of come together here, folks at the table. To really, try to map out the next steps. Where do we go from here? Because that was part of the original agenda that we would do that and come back together at around 10:30. I think we can probably wrap up by about 11 and get folks out of here early to go do whatever. but anyway, so so thank you for that really terrific discussion. I think things are really coming together. So we'll convene back here about 10:30, 10:35 or so, and. Okay, so how about we go into the breakout room? Yeah. One of the first ones. Oops. Okay, folks, I think we're about ready to wrap up. So if you, thanks for your patience. That's why we took time to put some stuff together. So we'll go ahead and do our last session here. All right. Well, thanks for your patience as we put this stuff together. So this basically is going to be a first cut at next steps, and it's definitely incomplete. Okay. And so what we want to do is just to kind of go over the high order points here. And so be assured that there are sentences to be written under each one of these that includes a lot of additional detail that we can talk about here. But we wanted to give you a sense of what we thought were the high order points, and then have you provide input on things that we may have missed, again, from this global level. The planning committee is going to be meeting for a few hours this afternoon to refine this and talk more about it and talk about the report and so on. But the first thing, of course, as we go forward is to discuss some sort of organizational structure. We're not talking at this point about something particularly formal, but if we are thinking about the kinds of things we talked about this morning, we need to have some sort of a framework of individuals who are potentially initially volunteering their time and eventually might submit a proposal to get funded to where they would get paid a little bit of time to continue some of the things that we're going to be talking about here in the rest of the list. But rest assured that it just can't be, sort of a willy-nilly thing. There's got to be some structure, some leadership structure and things like that would be put into place. And again, I always really like to come down on the side of something very informal and loose, very flexible. But as this thing might mature and go along, especially as funding might materialize, there would have to be additional thought given to specifics of that structure. But there's a lot of options there. So that's kind of the first point. We'll go through these and then come back and circle around with each one of them and get your thoughts. But again, there's a lot of stuff to be put under each one of these. Second one would be to identify the practitioner and user categories. And what that exactly means is yet to be defined, I think. But there are broad categories within, say, energy, within transportation, within the built infrastructure, the environment, so on and so forth. Urban cities, whatever, different categories of practitioners, and then the types of organizations that reside within them. Sometimes they're government organizations, sometimes they're military, sometimes they're private, sometimes they're municipal. And really try to get our hands around a very good question that was asking, what do you mean by practitioner and end user? And so given the fact that we see these as such strong drivers, it's incumbent, I think, on us to really put a lot more meat on the bone there and give that much more thought. So that's the second one. These go in some degree of order, though not entirely. The third one is we think about how this thing might evolve, collect and refine the use cases, which we did in a breakout, but there's a lot more work that needs to be done, and the data needs from practitioners and categorize those. So as we reach out to more practitioners, really get more specific about their use cases and their data needs. What is it you need? What variables? What time horizons? What duration? All that kind of thing. We did that in the pre-summit intensive, but we certainly can build upon that. So and categorize those. Translate those use cases then into model requirements. So this is that translation step to say, okay, this is what folks tell us they need. It's to John Town's point. Don't think about the computational thing. Tell us what you're trying to do, what you're trying to achieve. And so turn that into, okay, what would the model have to do to meet the needs of those use cases? Then translate those use cases also, these are kind of in parallel, into things related to data. We always talked about data, and data is very important. So accessibility, the characteristics of the data, the input to decision support systems and tools that a variety of users might use to access and make use of the data rather than just, hey, here's a netcdf file or something like that. So data is a very, very key thing. So we thought that was an important next step. And then along the lines of what John Schaaf has already been doing, continue refining this spreadsheet performance model. And he has plans to compare it against actual instrumented codes and paying attention to a lot of things, but we just called out this one in particular, which is important, the time steps of the various components, and in fact, the occlusion of various components. Maybe the time steps of ocean and ice might be changed. You might use different physics or whatever under different circumstances. And right now he's got some pretty decent user requirements, but I think he would benefit by having a more refined set of that. So to help John and get more accurate information and so on to profile what is actually possible or maybe not possible, the things we talked about up here would inform and enhance his work there. And then build this. Don't worry about the wording because we put this together quickly. But this idea of a community of practice for stakeholders and practitioners for folks like Edith and others who were here that said, I don't know quite why I'm here. I mean, even though we talked to them in advance, they felt uncomfortable, and I think there's a certain value in that. But I don't think we want that to continue. We want to have this community of practice where the stakeholders, practitioners, end users, whatever you want to call them, come into appropriate meetings like this one, and maybe even professional conferences or whatever, to learn, to provide their input, so that we build this closer community of practice. And that's something we talked about. It could be a takeaway. And then likewise, there's similar kinds of interaction already happening, has been for a long time, of course, years, between hardware developers, system architects, and climate modelers, the modelers more broadly defined. But probably the need to enhance that interaction along the lines of what we're talking about to make sure that there is a clear sense of where the community is going, what some of the pain points are, and so on and so forth. And that, of course, feeds off of the requirements being developed by John and some of the user needs and so on. And again, this is happening. It's not like this isn't happening at all, but we feel like we could maybe, juice it up a bit. There are, of course, existing organizations like the World Climate Research Program, Digital Earth, and many others that we could reach out to talk about how we would kind of envision a unified or a united community approach if we were to pursue some type of big initiative and make a pitch to, say, different types of non-traditional funders, what that community would look like. And I'm not talking about the practitioners. I'm talking now about the organizations that are developing kilometer scale models, other organizations that already have built communities across the world. We don't need to do that again. We can leverage those existing relationships and so on, and to kind of bring this concept into the fold for what they're already doing. And then finally, and I don't know that 10's a magic number, that's what we came up with, but obviously the messaging is important. And depending on who you're talking to, how you portray the message in the world that they live in, it's like very, very important. If you talk to a member of Congress versus a staffer versus somebody else, you have to do your homework and figure out what they're concerned about, what world they live in, what are their priorities, how do they think, and so on. And so that's very, very important here. So especially for potential funding organizations, but for everybody involved, thinking about the different audiences and some of the compelling reasons of why the stuff we're talking about here, which of course is very much inclusive of AI in all the different ways we talked about, will lead to a transformation. And I think to Tapio and other people, they said it right. This isn't about incrementalism, it's about transformation. And so, in some cases, we would need to make different arguments in different ways about why this is important. In some cases, showing evidence from work that's being done at MPI and within NICAM and other things like that provides very tangible examples of what is possible. Other people might be persuaded by other arguments. And so we have to really be thinking hard about that and what approaches to use and so on. So those are the 10 things that we came up with, and I'll kind of put them all on one page now, as being some of the top line things that we would think to do as priorities coming out of this meeting. Of course, writing an NSF report is one of the outcomes to talk about what we discussed here and so on. And so let me try to get that all on one page, and then we can just open it up here for discussion. Let me, before I do that, just ask the folks that were involved with this, do you have anything to add here? Anything that I misspoke? Maybe this is too small for you to see, but probably is, right? Let me put it in 2-page view here. I think we can do that, and see if there is anything you want to add to that. See if I can get this to work. Why is it not doing 2 pages? Oh, because side to side. Is that here? What's that? A little more to the right. This one? Oh, side to side. Okay. Gotcha. Okay, so I'll split it here right down the middle. Okay. And I'll make it bigger. Oh, there we go. Okay. And while I'm mucking around with this thing and making a total, what of myself, anybody else want to add to to what I said here? Who was in the meeting, and then we'll kind of open it up. I'm trying to blow it up, but it's not doing that. Anyway, hopefully that's helpful. I don't know. Anybody who's in the meeting want to add to this, elaborate on it? Okay, so let's just open it up for discussion. What have we missed, or maybe things that you find unclear or whatever? Again, recognizing this is just a really high order bits of this thing, but yeah, Trent.
All right, I got notes this time.
Okay.
Yeah, no. Okay, so on so both of these points have to do with stakeholders.
Okay.
We know we have stakeholders who have varying capacities to work with climate data, but high capacity should not be mistaken for high priority, right? Like the capacity of the user does not mean the priority. Unfortunately, when we invite stakeholders into our discussions, we often get and hear from disproportionately high capacity stakeholders, but not high priority. And one of the same sometimes, but
right.
So to assuage that, I would say number 7, we should build a framework for bringing these discussions to the stakeholders. Because we have representatives from what I would consider low capacity stakeholders, representatives like Edith and Jean, and it's great that they're here, but I don't think we can depend on folks like that for all of them. So that's really important that we can bring this discussion to those meetings, something I talked about on the first day. The second thing that I haven't heard about in really any discussion this whole meeting is equity in these. So how do we reach those stakeholders who can't even begin to understand, visualize what their data needs are because they have been historically either underserved or not served at all by climate services.
Good
So
point.
that's just 2 things.
Yeah, thanks. No, that's great, Trent. Thank you. Okay. Good. Great point.
Kelvin, I thought you did a great job summarizing the discussion we just had and also what the important next steps are. And I was wondering if perhaps, I realize I didn't raise this during our meeting, but would it be important to also have some next steps on how to find the points that we do agree on in terms of the scientific approach? And I don't mean to put anyone on the spot here, but perhaps folks like Chris Brotherton or Tapio could speak to what a potential way to do that could be. My first thought is like perhaps sending a follow-up Google form or something and see where we align and where we disagree, but that might be naive, and I welcome thoughts on that.
Yeah, absolutely. In fact, that was sort of, that's implicit, but I'm glad you mentioned it because that's really sort of foundational to the NSF report of that session we had this morning of capturing all that. Okay, what is it we agree on? And frankly, we agree on pretty much everything. There were a few points of scientific discussion, which I thought were fabulous. As you said earlier, Maria, that it's good that we don't agree on everything. So yeah, that definitely is part of summarizing all of that stuff. So I can certainly put that on there and should and will, yeah. So I'll say summarize the meeting, and that includes all of the above stuff. Is that okay? You cool with that? Okay. All right. Great. Yeah.
Yeah, so I don't think this is a disagreement to what Trent said, but I think there might be a different way to think about it. And it really comes from I won't beat this up because we'll have more conversations later, but making decisions with climate information is really not the same thing as making decisions with weather information at all, even in its simplest form. And so whether you're a high capacity user or a low capacity user, borrow that terminology, I know what you mean by that. The reality of the situation is that there has to be somebody in the way who is often called these days a translator.
Right.
But in practice, what that means is an expert user who knows something about climate, right? And there's a huge lack of those kinds of people generally across the world, right? Which in some ways is a big problem in itself that this effort is not going to solve in 5 years. On the other hand, from a practical standpoint, it offers some opportunities, which means you can probably shortcut a lot of these discussions about engaging stakeholders and get to the people who really are the translators, because they understand the use case a lot better. Now, the equity problem is a separate challenge because there's probably multiple layers of translation needed in that. But still, the people interacting with the output from this are going to be experts, right, at the end of the day. So I think just keep that in mind, I think, going forward, because it may structure how you cut through this in a way a little more efficiently. I'm not saying we ignore the billions of end user cases, right? Because there are many, many, many of them, but I don't think that's the hard part of the problem, identifying those. Like we could sit down for a couple hours and write 100 of them, right? So
Josh, could you give an example of translators just to make sure that everybody's understanding what you're saying?
So I think, and I'm going to leave the disadvantaged community translators aside for a minute, because I think that's more complicated. I mean, I think maybe the best analogy we have in here is Gene, but I apologize if I'm missing somebody here. But those are people who are boots on the ground, who are experts in their community needs, not necessarily experts in the science, the climate science. And so you often have to have that other expert in the way, right? So there's a value chain to get information to them, right? Direct access to data is just not going to help because the decision space is way too complicated, right? So So experts who are experts out there and outside of that world, more and more we see companies who are trying to make complex decisions based on climate information bring in climate expertise to be that translator.
Right.
That's one class. Another class is they go to consulting companies that may or may not have real expertise in this, but they'll always claim they do. And then there's a lot of translators sit in universities, right? But they're not, their reward structure doesn't allow them to really serve that role on a sustained basis, right? So, and then there's unusual translators like us, but we're not even consultants, right? So we still need consultants in the way in our value chain in many cases, or a translator in a company. But
yeah,
so I don't think there's one kind, but the common thing is that they know something about climate, right? And how to deal with a lot of data and things like that. And I think it's just another way to stratify this. Like, what is a user category? There's experts and there's non-experts. That's like the general way of thinking about it. And I think you're going to get a lot further in this, really focusing on the experts, because the reality is that the experts are the ones that are going to be interacting with it. And experts, by the way, a lot of it includes science and the research that this can empower, right? I mean,
for sure, yeah.
That's a whole other user category that's maybe so obvious we don't even have to talk about it. But anyway, I don't know if that made any sense, but I can go further on this at another time. But,
no, that's very helpful. Yeah, yeah. That's really good. Oops.
Can I just sort of clarify and condense what you said about translators? And to me, the translator is somebody who takes the information, whether there's expertise or not, and converts it into actionable, right, strategies. I developed a plan. Gene will communicate and turn it into policies. Those are the translators you need. So regardless of sort of our capacity to fully digest all the information, but that gives us the sort of expertise.
Right. Yeah. Yeah. Gotcha. Yeah, no, that's a good point. That's a good point.
I think one thing as well is not to underestimate the amount of resource that's needed actually for that translation role, because it's often not thought about. I don't think, I mean, maybe it isn't climate scientists who should be thinking about this, right? But there's this lack of funding for actually that actionable information production generally, and certainly in the UK where I am, you know, the latest climate projections very much, you know, you can download NetCDF files. It's not really what's needed by users. So it's that translation piece that actually is needed as well in this fund. If you're looking for funding, philanthropic funding, then actually it's really important that it also includes this kind of work as well.
You know, NOAA put out a solicitation some months ago about the future climate workforce. And it seems to me that that's an area that really hasn't been really focused on, right? I mean, you're not a dyed-in-the-wool climate scientist. You're not somebody who's developing policy for a municipality. You're somewhere in the middle. But am I wrong in thinking that there aren't? I mean, where do those people come from?
Yeah, I mean, I suppose in the UK, a lot of the expertise in this comes from the Department for the DEFRA, basically. So the adaptation people there.
Yeah.
So thinking about climate resilience, they're trying to basically get this information produced. But I think the problem is there isn't a lot of expertise in this area, actually. So they go back to the Met Office and the services like that, the climate scientists, and say, can you produce this information? But actually, they don't know really what's needed. So it is this co-creation that's really, really needed. And this certainly is something that we're thinking about for the next set of climate projections in the UK. Rather than just having an advisory committee of stakeholders that give advice on what outputs are needed, which is kind of where we are at the moment with this, right? It's very much about co-creating information and outputs, because it really matters what format those things are in, and data streams that you can produce that immediately can be ingested into models that people use in the real world is really important. So they don't have to do that data format changes and all of that kind of stuff too. I think you can streamline these type of outputs so that you can have a real impact on the real world very, very quickly if you actually co-create the information needed.
So it really brings up the important point that was mentioned about whose responsibility is this stuff. So if you have sort of climate modeling community doing things, running maybe quote semi-operationally or whatever. Then you have data scientists who are taking that stuff, manipulating it, and then you have a translator who's taking that and translating that stuff into an end user, application, right? Potentially, there could potentially be 4 steps in the process, right? Creation, the manipulation in terms of a data scientist, then okay, hand that off to a translator, then the translator translates it to here's the person that's actually the farmer, the rancher, whatever, or the organization that is supporting the farmer or the rancher. Is that right?
It's still a very top-down approach, that though, isn't it? So
yeah,
I mean, it's for me, it's much more about a circular approach where you're actually thinking about what are the types of decisions that need to be made, right, by different sectors, and therefore what types of products and information are needed, and can we provide that? And then how do you provide it in the best way? So it's very much a bottom-up approach, actually, in some ways, but it's definitely something that needs to be co-created. So it'd be about having those translators, whoever they are, right, who have the expertise in the stakeholder decisions, the ones that are needed. They collect that information, and then they work with the climate scientists to actually produce something, something actionable.
Right. No, that's great. That's a very good point. Yeah.
Translators, I hear people discussing about the translators. I feel that we may complicate the matter here. Yeah, you really think about it, and then for those high capacity, let's use the word stakeholder. Yeah, say insurance, reinsurance companies, particularly the big ones, or large energy company, for example. Don't think they don't understand this. Yeah. And don't actually perceive that I am the expert and I need to educate them. As a matter of fact, that's not for, maybe for too long from them. I mentioned yesterday, and then there is a friend of mine who is actually the head of an institute on natural disasters, primarily with weather. And he wants to understand what's actually the disaster, the statistics, the data, things like that. You know what his source is? It's not any meteorological agency. It is a reinsurance company. I asked him where you got the data. He said, your company, as I didn't know that.
Yeah.
So really, we need to humble ourselves, quite honestly, and otherwise it is going to be cut off, honestly. It's for the high capacity stakeholder, they really know, and for a long time, they may not have the kind of granular information they actually would dream of, but they have spent so much time coming up with certain ways in order for them to have a approximate solution. They're understanding not only on the impact of the events or the occurrence of the event, the statistics of the event, and things like that, and also how to approximate that, far exceed what we might have imagined here. Yeah. So that particular what I see, the primary need for the translation is really think about that. But we are here, we're thinking about the model. We are the modeling expert, and they really understand the phenomenon, the requirement, and they can even talk really in expert manner. The key is how to translate that particular one, translate use case into model requirement. That's actually what's needed. Yeah, it's a dialogue. Really, it's dialogue.
It's a dialogue.
It's not in the role we need to create right now, because they already exist.
Yeah, it's an iterative process, but I do think that well-resourced organizations, like you say, can do that. But I think the point about democratization and equity is really critical, and there are a lot of folks that don't have that capability. And that's part of what we want to do, is to democratize and reach out to those other groups and organizations that aren't so well equipped, because they tend to be at risk the greatest, I think. So yeah, go ahead.
So I'd like to just dig into number 9 here, and I'm not sure if there's other. So it's number 9. So So I think there are a few things missing there that I would flesh out. First off, it's also software developers and people working on software frameworks. So again, it's computers, to me, it's computer scientists working on both hardware and software that need to be dealt with there in terms of interacting with not only the climate modelers, but also the data scientists that are doing that interpretation layer. right? So again, with the hierarchy, there are a couple of places we need those interactions, not just in the one.
Yep.
Climate model one may be one of the more important ones, but I don't think we should forget
Mhm.
the interpretation.
Oh, that's a great point.
The
Yeah.
other thing I will just ask, so I know you guys are going to go and prepare a report. Is the Nucleus team going to have an opportunity to review that?
Yeah, absolutely.
Yeah.
Yeah, that was something that I sent in a message long ago, but you guys have been blasted with so many emails. I think you probably didn't see it, but yeah, absolutely right. Yeah, go ahead.
I wanted to add to the equity point and just connect some dots in the
Hang on, guys.
connect some dots in the discussion that we've been having, in the sense that a lot of the things that we've been talking about are sort of assuming that we have the people to do them.
Mhm.
And I think we're talking about a workforce that doesn't necessarily exist yet.
Mhm.
And the vision here, I think, could really be complemented by also having a vision for how to maybe develop educational materials, or, actually offering the compute that a lot of the students, certainly that I work with, could
Mhm.
benefit from, of having, the data co-located. And I think there's really an opportunity here also for catering to our needs, in terms of, we need the people to actually do these things, the translation, but also the coding and, the development in a lot of different aspects of this.
Mhm. Absolutely. And that was one of the included in one of the challenge sets, is about the workforce and the opportunity. And I think again, climate and weather coming together in this kind of thing with these kilometer scale models opens up whole new vistas of education, not just in the atmospheric sciences, but in economics and lots of other areas. And we're seeing more and more cross-pollination there, but still we tend to be fairly traditional and stovepiped in academia, and the federal agencies certainly that way. So yeah, absolutely right. And I think that could be something that we need to make sure and put on specifically. I mean, it'll be in the report, but I think highlighting it here as a key action item is spot on. Yeah. Thank you.
So I think when we added data scientists to these interactions, I think we also need to think really about the data management. How do we describe the data well, so that the policies around data, and I don't know where this it fits there, but I think just the overall, again, AI lives on really well-described data sets. And again, we need to add that, I think, to the list of expertise, I think, that needs to be on the table.
There was something in data here somewhere, was it? Oh, translate use case. Yeah. No, I think it should be separate. Right. Right. I mean, when we first started this conversation, we said that it's axiomatic that these data ought to be, fully open. And frankly, thinking about philanthropic funding gets you away from all the craziness that's going on now in terms of discussing open access, open science, public access. I mean, there's a lot of dust flying around in the air about this with regard to different publishers, with the government policies. It's kind of a mess. And typically, if you're funded by a philanthropic organization, they demand immediate open access publication. That's just axiomatic for them. And so this is the kind of sort of red tape I mentioned you sort of avoid when you're doing something in a non-traditional way, which is a very positive thing. So yeah. Yeah, go ahead.
I'm struggling to phrase this in a kind of bullet kind of way, but I've kind of got this concern about this. There's a kind of gap between what we're trying to do here fundamentally and the user engagement. Because fundamentally what we're trying to do is, and we've all agreed, to do kilometer scale global modeling, we're trying to tackle some long-standing systematic biases. We recognize that it's not magic going to 1 kilometer. It's going to take a lot of work. So at the end of a long time, we might have a global model which is better. We hope to have a global model which is address some of these things. In itself, it's not really making available new products and capabilities. It's just making them better and better to use. And so, if we start too early to engage in, you can have some data, to get people excited about getting data isn't the right thing. The user engagement is trying to help us prioritize which of the systematic biases we really need to tackle. And so this service idea is, you know, probably really important, but it comes very late in the process. And the engagement process is much more about, well, what are our priorities in the systematic biases we're trying to improve?
Mhm.
I feel it's getting a bit lost, that key point.
Yeah, let's see, where was that? These are categories. We had something about where's the community of practice thing? It's these cases, more requirements. Anyway, yeah, that's something we thought about before and talked about is for those who use the information is that we're giving you basically the same thing, except it's a lot more detailed, it's more voluminous, and it's better, but basically it's the same stuff. So how much do you need to retool your CAT models, need to retool your statistics, all this kind of stuff? I think it's a really interesting question. And that's something I think that we really need to understand. And Josh and others that are here from those kinds of companies would be very interested to hear your thoughts. We did talk about the practitioner thing, didn't we, Francina? I thought, didn't we talk a little bit about, is it just more and better, or is it fundamentally giving you stuff that you're not now getting that will transform you?
Discussing. I mean, as the analogy that we're discussing right now is like the South America project where there's fundamentally different information that is being
But I'm just thinking in terms of, are they familiar with it? It's like, now we're getting 100 times what we had before, but it looks the same, except it's way better, it's more detailed. Or is it fundamentally somehow different? That's, I guess, what I was wondering. Now, we don't have to spend time on that, but yep.
Yeah, I mean, we already have to get hourly data at points. So we're making that up from, dynamical or statistical or AI downscaling techniques from existing models. So that format currently exists. It's just a question of whether you have accuracy and
like you guys use verify.
Right. Right.
And once you get the result of scale, then the prefix that you get is more similar to IME, which is right. So it's different. It's a different
There you go. That's a good example. Yeah. Yeah. Right.
I mean, typically we would do bias correction so
yeah.
But exactly.
Yeah.
So number 11, not only the reach out to the existing organization, maybe to invoke international involvement to maybe ask you to lead some international more enhancement of this kind of activities.
So let's see, let me find out where we say that. It's down here.
11.
How could we better say that to convey, or was it? It's, where do we have?
Maybe we are interested in access to the computer resource in here from the internationally, and also maybe to the activation.
So are you talking about the building the international community, or?
Yeah, maybe generalize 11, just not only reach out, but number 11.
Number 11, reach out to, okay. So, so engage maybe, or?
International involvement.
Pardon?
International involvement.
Right. Yeah, the word international isn't in there. That's a big oversight. Thank you. Existing international organizations. Okay. Yeah. Yeah, that was the intent. I'm so sorry. Somehow that didn't get in there, but existing international organizations. Yeah, that was the idea. Sorry. So thank you. That's very, very important. Yeah.
Coming back to, sorry.
Oh. Cool.
All right.
Go ahead.
Yeah, no, I was going to say, one of the things I think we haven't talked about at all, but I was mentioning this to myself and Andy were talking a little bit about this yesterday, is that actually creating a kilometer scale model would actually allow us to produce very high resolution reanalysis data as well, right? And it's an obvious thing. Like I've heard so many people in this room say we're using Era 5 precipitation. That horrifies me, quite honestly. It's really, really bad, okay? It's not very good anywhere, but it's really, really bad in the tropics. And it's really bad if you're thinking about extremes, and that's probably what you're using it for. And if your bias correct, great, but actually there isn't data in many places. So having, I mean, where these have been developed regionally, and there is one over Europe, for example, parts of Europe at least, they're really, really good. And they do then provide much better estimates. It's still a model, but it's providing a much better estimate of precipitation. You know, it's something we could then be using to actually, as a kind of substitute for data where we don't have data. So I think it's quite exciting prospect as well, actually, to actually do more of this like historical. Yeah,
that gets into the whole global data assimilation issue, which is itself could be extremely important in running these models. And so, yeah, we had talked about that in the context of training AI models, that they're now trained on either Era 5 or they're trained on forecast. There's been a lot of work done at the storm scale training these models based on high resolution model forecasts, but they're forecasts, they're not analyses, because the analyses are only done like every hour or something like that. So the forecast, you really get that fine scale every 5 minutes sort of thing. And so that's a really important research question, I think, but you're absolutely right. And that itself is a whole area of research, I think. So yeah, completely agree. That's exactly right. Yeah.
Just wanted to come back to point number 9. I think I'm a bit unhappy about the enhanced interaction, because that, right, I think it would be nice if there was something a bit more tangible. There's lots of, low-level algorithmic and implementation choices that can be made. Hardware has lots of widgets available that might be useful in this context, but nobody has had the bandwidth, the resources to actually go and try to use whatever tensor cores for a radiation scheme or things like that. So I'm trying to understand if there's a way of not turning this not just into a talk shop, but actually define some kind of a research agenda of, of topics that should be addressed with existing hardware, but with the flexibility of on the algorithmic side and from the modeling side, right? Because we can fiddle on the hardware as much as we want, but we need input from the modeling society or community to make the right choices there.
Or, wordsmithing. So develop a focused research agenda. For more effective interaction.
So could you educate me how that interaction happens now? I mean, back in the days when I was doing that sort of stuff, it was relatively informal, and people go to supercomputing and stuff like that. But how is there a focal point mechanism for this to happen, or
Well, it gets back to focused research agenda. If you get somebody on NV research that dedicated to the task, for example, and same with AMD, then you can have a very focused interaction. But that only happens if you engage on your side. You can't, if AMD calls and says, we'd like to work with you, and you're like, yeah, I don't have time this week. So both sides, it's great when the vendors engage, but you have to have the cycles freed up to engage with them. And the problem is that that's not always the case.
So is there a coordination mechanism that we're lacking also?
Yeah, I mean, this would have to act also as a coordination mechanism to ensure that you have a targeted and focused engagement. Right now, again, like you said, it's informal. It's based on people who are willing to free up the time on both sides to do these engagements.
I mean, even just a forum for discussion and stuff. And I mean, respecting the proprietary nature of different companies all getting in the same room and talking, but that can be addressed. That's not a
and also, I mean, at the user facilities, there are these things. What is it? Catalyst team, they call it at Argonne, or can't remember what we call it at NERS. Maybe Barb remembers. Anyways, there are at facilities, but I think you need to have it integrated into this effort. The facilities are looking at things that are big ticket items in their workload, and this may or may not make the cut for that. So it has to be a part of this activity to have a focused engagement
Yeah.
with the vendor community.
And not to put Mike on the spot, but did you want to comment on that? Mike Schulte, is he around? Oh, yeah. Yeah, I'd just love to hear. What- Okay. Mhm. Uh-huh. Yeah. And this might be, the thing that's out there that would, serve to bring people together, right? There's always stuff to be done, but this thing might be of the nature that would say, yeah, okay, we see this thing that y'all are trying to do. Let's it's tangible, right? Versus, hey, we just, we want to get together and talk about the simulation that my research group and I are doing. That's a whole different ballgame.
No, it requires effort.
Yeah, sure.
It can't be casual.
Yep.
Okay,
Yeah.
come on.
Yeah, and I think this is the type of thing that it's exciting enough that you could likely get a lot of different vendors to step up and
Okay.
be willing to engage in conversations. And I think especially for certain things, there are a lot of good discussions you could have between multiple vendors and practitioners and scientists, et cetera, that you could do without NDAs.
Oh, I see. Right. So we need an NDA. Yeah.
And
Mhm.
this is something more speculative though that we've been working on with AMD and NVIDIA, research, which is to be able to create a proxy that uses open source stuff, because we don't want to see their trade secrets or any of that stuff. Set up an experiment, but do it documented well enough that they can reproduce that experiment using their own internal stuff. And so we've been doing great work with Larry Dennison and with AMD, Bo in AMD, where we construct an experiment using our open stuff, but we know that their stuff's way better than our stuff. And does that experiment pan out when you actually have?
Yeah, sure.
Yeah.
No, thanks, John. Thanks, Mike. Yeah, go ahead.
So I think we need to strengthen number 11 from reaching out to international organizations to including them as really active members of a potential international project and doing deep analysis of what they're doing, what information they've already collected from classes of stakeholders that this would target, and seeing how to build upon that and do more than they're doing so that collectively as an international project, we all get there sooner. So more than reach out, bring in.
Okay.
Particularly the destination Earth and the Eve stuff.
Right. Yeah. Yeah. We were kind of trying to count them up, and there's a bunch of them. Okay. Yeah. I think we'll wordsmith it, but I got your point. It's a really, really important one. And we didn't want to presuppose anything, so I think that's why we were a little squishy with the wording to reach out. But we want to just be bringing in existing international organizations too. Yeah. Anyway, we'll wordsmith that, but I think it's a really good point. Yeah.
And yeah, I just wanted to add to the previous discussion on this co-design topic. So something that, and it's very pragmatic thing, but something that really works well to get the industry engaged is to get very key use case included in the benchmarking for the procurement of HPC systems.
Mm-hmm.
I know this is very pragmatic, but that's the way it works really. So that's the way you get the industry engaged in helping codes to go further. This happened with ICON, happens with ProMax in the molecular dynamics. That's how codes get so important and relevant for them to justify the effort they put there.
Yeah.
If I can respond to that one. Unfortunately, at that point, it's typically too late. And that it helps. Yes, it does help to have this type of challenges that you put out. And then on our side, we're starting to optimize or do whatever is needed, to make this fly. But I think for many of these cases, for the interesting cases, there needs to be algorithmic flexibility. And that's algorithmic flexibility that's only feasible if we have the modelers and the domain experts in the room, right? And so this cannot happen as part of the procurement process because, we cannot start modifying the essentially the model that we're using. But there are so many, I mean, so much flexibility in some of these models that if you're just implementing what has been given to you so far, well, you're limited in what features you can use of your hardware. But if there was a little bit of give and take on both on the software side, on the side from the modeler's perspective, it could fly on existing hardware.
Fully agree, but I also think that there is a role, I think you mentioned that, John, for the support teams on the HPC centers that can work also closely in this code development. And then industry, of course, can play a role, but it's also easier, I think, for you if it's clearly identified that the code is at a stage where it plays a role in the procurement later on.
Fully agree. Yeah, I mean, we need to know the context of why somebody comes along and says, hey, let's discuss the radiation model and let's figure out if there's a new way of writing radiation. But again, exactly, radiation is I think, a nice example where, it's super heavy duty, it's important. And yet, I mean, there's lots of cheating that happens in that algorithm. And so if we can talk to each other, right, that not just somebody comes along and says, it needs to be exactly this scheme, maybe we can make it fly better on existing hardware.
Yeah, and I just wanted to point out that this was very similar to what we did under the Star Forward program. So early on in the exascale computing program is we had what were called proxy apps, which weren't necessarily the full application, but they were representative of it. And we were able to do things like run those applications on our simulator. But then even more important, we could sit down and we could talk with the scientists that had worked on the applications and talk to them about, okay, well, we're thinking about making this change to our hardware. Does that make any sense? Or we're thinking about, this potential change to the underlying software, the algorithm itself, or they would come up with a new algorithmic change. So I think lots of times by having these example codes, you can get into very, very pragmatic looking at, well, what if we make these changes? How would things vary?
That's a great point. Star Forward, yeah.
So Kelvin, we touched on this a little bit yesterday in one of the breakout reports from our group about equity, and had a very nice statement about incorporating equity into all the choices we make. I'd like to expand on that a little bit. The harsh reality is that the impacts of climate change are felt most severely by the poor, whether those poor people are in our own country or abroad. And so I think especially about the global South and developing nations, we should consider how we can engage scientists and both social scientists and physical scientists from those nations. And I think we have an ethical and moral responsibility as in the United States, being the country that is most responsible for climate change through our emissions, although the Chinese are working hard to catch up, that we need to do this. And that is important in many ways. I would mention the UNFCCC Conference of Party Loss and Damage Fund, which potentially could involve trillions of dollars. And I've written some opinion pieces about how we should consider how we can inform those decisions with the best possible science. And I believe that this effort could aid in that.
Mm-hmm.
Thank you.
That's a great point. Yeah, absolutely. We're about 11:45 here, almost exactly. This has been wonderful. I mean, great points. And although we're not going to share the whole NSF report with folks, we will with the planning committee, they'll write it, and the nucleus team will certainly give their input and edit it and have full it kind of impractical to send it out to everybody. What I would love to do though, and I think if it's okay with you all, because this next step stuff, I could see it being blown out to like 3 or 4 pages of text. If you wouldn't mind, I'd love to send it out to you all, because if we are going to build a community, we need your input, and you need to know that we value your input and we're going to listen to what you say. And if we get this wrong, and you come away saying, well, that's not what I heard, that's bad news, right? So if it's okay with you, and we have all your email addresses, we'll go ahead and send this particular part of it, the next steps part, to you all and get your thoughts on it and make sure that it's just right, if that's okay. So any other final comments? Super helpful. Well, I'm blown away. And so I learned so much, and I'm so grateful for all the time that you have spent. As Maria said, you know, taken probably 4 days out of your life to come here, and I hope you do feel it was worthwhile. And we actually do. Let me try to get down to this. We do have a so-called satisfaction survey here that we have put together to allow you to tell us what went well, what didn't go well, how we could do better, and so on. Some of the things like the crazy Zooms were policies of the university we didn't have any control over. It was a little bit difficult and cumbersome, but there's a QR code for you, and this thing is also on the Summit website, Deanne, under resources and read aheads. It's a relatively short survey. It's all little dials, little buttons you click and stuff. It's like 15 questions. Check boxes. There's a last one where you can provide your comments and stuff, but you know, but we will look at this and we will report these results directly to NSF unchanged. They'll get the raw data with probably in some graphical format or whatever. We will tell them exactly what we. They are anonymous, right? Yeah, they are anonymous. And if you want in your comments to say if this is who I am and contact me because I'd like to follow up, we would love to do that as well. But we are through this big organizational structure at NCSA that helped put all this together, all the logistics and stuff. We will do some postmortems. And so if you have things that we could, you know, that we may not be aware of, that you pain points, things you ran into is like, gosh, don't let this happen again. Please let us know. Big rats in your room or something? No, probably not that. But but anything like that, we would love to know to make sure that it gets fixed, right? So anyway, any final comments? Well, I think lunch is out there. Box lunches, gourmet box lunches as always, yeah. So, well, with my profound thanks and that of the planning committee and the Nucleus team for the tremendous time and intellectual energy you gave to this. God bless you. Thank you so much for all you've done. And we'll be in touch and we'll send you out some stuff to follow up with. And John's running the microphone.
So before you completely close it up,
yeah,
I want to express my thanks to you for all that you've done and the leadership you've provided in all this.
Thank you so much, John. Appreciate that. You know, working with a great team is incredible. But you know, just learning, I have learned so much here. So you know, I hope you all have a great rest of the afternoon. And if you have any logistics issues you run into with flights or whatever, let us know. What shuttle information, right? Mm-hmm. Yeah, really. Absolutely. So for the planning committee, we'll reconvene about 1 o'clock in probably the room that we were in to prepare the next steps. So take a breath, go to your room if you need to or whatever, and we'll start about 1 o'clock. And so please make sure you get there. We should be done by 2:30, maybe 3. So, all right, great. I'll leave this up here in case you want to refer to it, but feel free to just enjoy lunch and safe travels back home. Yes.
Rudy and Mark and figure out what our next play is for that. Yeah. I have some stuff I got from Paul Woodward that I need to check in the spreadsheet, so he identified.